class, we talked about linear transformations. In this class, we'll talk a little bit more on linear transformations before we move on to matrix theory. So, in the last class, we were talking about. We did mention that a set of all the transformations which are mapping V to U. That's sort of all the transformations which map V to U. So all these transformations, they also put together, they form a vector space given the spatial definitions of addition and scaling that we had defined. So now the dimension of the vector space is given by the product of the dimensions of the mapped spaces. So dimension of that mapping space is going to be given by dimension of the vector space V multiplied by the dimension of vector space U. So put together, that gives you dimension. A quick way to see this, or rather sort of roughly to prove this, a formal proof can be constructed on similar lines. So we'll just look at a very quick proof. A vector, let's say a vector V of the vector space V is getting mapped linearly. Okay, it's important, linearly to a vector U of the vector space U. So let's say we write in general form in terms, if we choose V1 to Vn as the basis, V1 to Vn as the basis of for generating the vector space V, then any vector V of vector space V can be written as a summation of a linear combination of these vectors, lambda k, Vk. And similarly, we can choose U1 to Um as the basis for the U vector space. And so we can write it in terms of linear combination of those vectors in this form. Now let's say we take one sort of linear transformation A, which belongs to that set of linear transformations. It's one of the elements of that set. Let's say we use that to transform V to U in this fashion. So since we can write V as in this form, a summation of k equal to 1 to lambda k, we will use that definition here. So A operating on summation of lambda k Vk would be given by, you can take it inside, summation lambda k A operating on Vk. So that's how it will look like, and that's what is written here. And that's going to be equal to pure U vector. Now, let's say if we define these spatial mappings, AV1, let's say each of these basis vectors that we have taken, how do they map with respect to the mapping A? So there would be AV1 would be something like some U prime, which can be written in the linear combination of the basis vectors U1 to Um. So we use that construction here. We can write this as alpha 1 to denote this, that is for this mapping, and S, which is going to run on the basis of U vectors. So you can write it this way. Similarly, AV2 can be written as alpha 2 S US, right? And now if we plug in these definitions for all the basis vectors of V, if we plug in this representation into our original expression in this way, we will be writing summation k equal to 1 to n lambda k, and avk now we are writing in terms of US vectors. Now we can pull out this summation of this k and send this lambda k inside. So it will become summation over k equal to 1 to n and summation s is equal to 1 to m lambda k, which represents a specific vector of v that we have taken, and this combination of alpha ks us. So in a way, for any general mapping A, what you see is that these numbers will change, alpha ks. And the way you can choose these numbers is k running from 1 to n and s running from 1 to m. So the number of values that you need for to represent any generic mapping, you need to define these n into m, which is coming from this numbers or values, and n is nothing but the dimension of v, and m is dimension of u. So these values need to define, and so that will define any generic linear mapping. So from here you can conclude that the uh, dimension of the vector space of all the mappings v to u will be equal to dimension of v into dimension of u. And as I said, this is a sort of a quick way of seeing it. It's not a very formal proof. A formal proof can be constructed on similar lines. Now we'll move on now to the definition of a transpose. So for matrices, we say A, we know what it looks like. We know how to get A transpose by saying Aij will become Ajith element of the transpose. That we know for the matrix theory already. But for any generic linear transformation, which is like a mapping between any two vector spaces, we can define the transpose, and this definition of transpose is specific to inner product spaces, the vector spaces which allow inner product to be defined. Then we can define transpose or the adjoint, it's called. One should not confuse it with the classical adjoint, which is a matrix of cofactors, transpose. So that we'll get to later. But this adjoint is not the classical adjoint. So this is adjoint or transpose. You can think of it like a transpose. So for real vector spaces, which you have already seen previously, they are all about. Therefore, we call them transpose. It's a normal name that has been chosen. So to define the transpose or the adjoint, we say that a given linear transformation A, which is mapping V to U, sort of another mapping can be defined, which is a mapping from U to V, reverse mapping from U to V, and we denote it by choosing the star. You can also write it as a transpose. That's what we will write for real vector spaces. But in general, that's the notation that has been chosen. It's very commonly used, star notation. So, especially for complex vector spaces. Now, the way it is defined is this mapping is not just a random mapping from U to U, it's closely associated with the mapping A. So A and A star, they go together, and the way they are joined together in the definition is by this requirement, this condition. The condition is a dot product in the U vector space between the mapped AV vector is same as when you map U to V vector space and take a dot product with V. So on a Venn diagram, I'll represent it this way. So let's say you had this V vector space and this is the U vector space, and you're mapping a vector V using A, you're mapping it to vector U. Now, if I take U and use A transpose, I'll land up somewhere else. Let's say here V prime, and this I get using A star. So the dot product between let's say this is different u, this is u prime. I should write this as the mapping is essentially of u. So this requirement of this expression is that u dot u prime should be same as v dot v prime. Okay, and this is how you can sort of define the transpose. And this is for every u that belongs to vector space u and every v which belongs to vector space v. Now the theorem is that for every linear transformation of this kind, there will exist, okay, first is about existence and the second is about uniqueness. It exists and it is unique, a linear transformation or transpose which is from u to v such that u dot av is equal to a star u dot v. We'll not look at the proof of this theorem, we'll just look at the properties of the transpose or the adjoint mapping. So A plus, if you have two transformations, you pick from mapping, so A comma B here, they belong to the mapping V to U, and A star and B star, they belong to the mapping set of mappings from U to V. Okay, so this addition is in this space and this addition is in this vector space. Okay, so that's the condition. Now, if you take AB and take a transpose of that, that will be equal to B star A star. So again, we can quickly see this from by looking at Venn diagram. Let's say we have B, U, and W. The way we have written, we are defining this as our B mapping and this as our A mapping. Correct? So B belongs to the vector space of mappings V to U. A belongs to vector space of mappings U to W. And together AB would belong to, this is your A B mapping, which will belong to V to W. Same way, A star would be a mapping which will take you from here to here. This is your A star mapping. And then this is your B star mapping. So clearly you can see that when you're going, you would be operating B, you take a vector V and operate it with B, you will get a vector of the vector space U. Then you operate it with the mapping A, you will get a vector space of W. So this belongs to U, and eventually this will belong to, I'll say, this is not vector, this is vector space, so it belongs to the vector space U, and this belongs to the vector space W. And when you're coming back, defining the transpose from W to V, you will first operate A star on a vector W. This will give a vector that belongs to the vector space U. Then you will do the transpose with on top of this, and this will give a vector of V. And therefore, from here, when you put together these things, you will say AB star is nothing but going to be B star A star. Okay. So if you scale lambda with A and they could take a transpose, you will have to remember that you get, in general, for a complex vector space, you will have to take a transpose would require that the scaling should be taken as with a conjugate. This essentially comes from that inner product definition, the complex commutativity requirement or property of inner products. That's where it comes from. So this you'll remember for complex vector space. For real vector spaces, of course, it doesn't matter. You take the transpose, you get lambda A transpose. That's what you get, right? You'll get this there for real vector spaces. Now, you have, let's say, if we talk about these spatial mappings, which are mappings from V to V, then the transpose mapping 0 would be same as the 0 mapping from V to V. So if you're taking this as V and this is also V, let's say, and you're mapping this from here using, of course, if you say, let's say A mapping, then you can come from here to this side, which is A star mapping. Now, 0 mapping will map everything to 0. So 0 transpose will also map everything to 0 on the from right to left. Same way, this identity transformation that you have, which is I times V will give you V, that transformation. This transformation is such that your I star, when you operate on this V, this will give you the V back. So there's a direct correspondence between the two. Now, if you say you take A, you're mapping, let's say, V to U using A, you take the transpose, you go from here to here somewhere, let's say A star, okay, right? And then you say you're going to take A star, and then you take the transpose of that, you will end up back here. So that will be the same as mapping. So if you have a mapping which is A star of B, that will be same as saying A of B. Okay. So that's what it will mean. So essentially you will have, that's the mapping that you get. So if A is non-singular, if A is non-singular, then you would see that A transpose is also going to be non-singular. And then the inverse of that mapping you can define as A transpose inverse is same as A inverse transpose. So for real vector spaces, we write it this way. A transpose inverse is A inverse transpose. Okay. So these are the properties of that joint. Now, the range and null space properties of these linear transformations can be listed down in these ways. This is like the vector space V can be generated and is essentially the range of A transpose and a direct sum with the null space of A. That's how you can generate V. So those vectors which do not belong to the null space of A, they would belong to the range of A transpose. Okay. Similarly, for the vector space U, it can be constructed. It's a direct sum. The vector space U is a direct sum of the null space of A transpose and the range of A. Now, this direct sum means that range of A star intersection of K of A is essentially only one element. That's one of the property, one of the requirements. And the second thing is that a vector V belonging to the vector space V can be split into two pieces. You can say as V1 plus V2, and this you can do uniquely in such a way that V1 belongs to range of A star and V2 belongs to the null space of A. Correct? So to prove this, what we do is we sort of first will prove this requirement that there is, if you pick a vector, it will either belong to a range of A star or K of A. That means it cannot belong to both of things. There is no overlap between range of A star and the null space of A. To show this, what we do is we take, let's say we take a vector V1, okay, and another vector u1 in such a way that, of course, this mapping AV1 gives you u1, okay, and we pick another vector u2, which is mapping u2 to v1. So if I have to show this on Venn diagram, what I'm doing is I'm picking a vector v1 here and I'm mapping it to u1 here. Then I'm picking a vector u2 here. This is mapped through A, and I'm mapping u2 to A star. Using A star, I'm mapping it to v1. Correct? So A star will not map u1 to v1 clearly. It will take it somewhere else. But we can take another vector u2, which will map it is getting mapped to v1. Now, what he's saying is, let's say if if we have picked u2 such that it belongs to the null space of A star, then this mapping A star u2 will be 0. And this would imply that I picked v1 as 0. Okay. So, but if I'm picking a non-zero v1, and then what I do is I take a dot product in this fashion between these two vectors. I say that I'm looking at the vector dot product between u1 and u2, which can be written as u1 dotted with A star u, wait a second, I can write this as u2 dotted with A v1 from this definition. And I'm saying that I'm claiming that v1 does not belong to K of A. Okay. Then I can write by because using the definition of the transpose, one of the conditions for defining the transpose, I can transform this into A star of u2 dot v1. And that gives you this particular relation, which is v1 dot v1, which is norm of v1 square, right? So if we take v1 to belong to K of A, then your u1 will be 0. Okay. But then because norm of v1 square is u1 dot u2 and you're getting u1 as 0, then you're saying that the norm of v1 square is 0. That's what you're saying. And norm of v1 square can be 0 only when v1 is 0. So if v1 belongs to the null space of A, then v1 has to be 0 if I subject it to the above condition. So that means a non-zero v1 belonging to K of A cannot be in the range of A star, right? That's what it would mean. And this would, you can immediately conclude from there that the range of A transpose or A star is sort of, there's only one vector which is in common, which is a 0 vector, right? So now this one part, first part we have shown now. this range of A intersection K of A is 0 that we have shown. Now the second part is to show that the vector space V is essentially range of A star plus K of A. That means the entire vector space V is nothing but vectors constructed by from the basis of range of A and the basis of kernel of A. Range of A star and kernel space of A. So these are the two set of this vector space V can be divided into. Every vector V can be constructed by basis of range of A transpose and basis of range of A. This is what we want to show now. Now to show this, what we do is we say that let's say we choose a basis, and we choose a basis in this form and arrange the vectors in this form, and we're not losing any sort of this. We are doing without any loss of generality. So we are picking vectors v1 to vk, which are the basis vectors for the null space, and the vectors vk plus 1 to vn as the remaining set of vectors that do not get mapped to 0 of the vector space U. So earlier we had already shown that the set of vectors, the map, when you map vk plus 1 to vn, we get these vectors avk plus 1, avk plus 2, and avn, which belong to range of A, and they also form a linearly independent set there. These vectors are linearly independent. Now we want to show that all these vectors vk plus 1 to vn, they belong to the range of A star. If we show that, then we can say that a vector space V can be divided into two pieces, which is range of A transpose and plus K of A. Now to show this, we'll pick a special, we'll say that, let's say AVK plus 1 gets mapped to UK plus 1. Similarly, you can say AVK plus 2 is getting mapped to some vector UK plus 2, and so on, till A of Vn, capital N, getting mapped to some vector Un. So this set of vectors we've obtained, they belong to range of A, of course. So in a way, what we are saying is the basis for range of A is given by the set of vectors UK plus 1, UK plus 2, and so on, UN, right, which is coming from here, right? So they're all linearly independent. Now we map these back using the transpose to the vector space V. So we say A transpose of A of VK plus 1 is going to be given by A star of VK plus 1. Now we take a dot product with VK plus 1. We get VK plus 1 dot with A star of A of VK plus 1. And that will be VK plus 1 dot A star UK plus 1. And that is nothing but saying is we can just take it this side. We'll get this as A of VK plus 1 square, norm square. Norm square means, and because VK plus 1, A VK plus 1 is not 0. This is not equal to 0. That means this norm has to be greater than 0. It cannot be equal to 0 also. So this norm has to be greater than equal to 0. Going by that, we know that we say that now VK plus 1 dot of A star UK plus 1 is greater than 0. That means none of the two vectors can be 0. That means A star UK plus 1 is not 0. That's what we have gotten, right? Where A star UK plus 1 belongs to range of A star, right? Now we can show that the same thing for A star UK plus 2 is not equal to 0. A star UK plus 3 is not equal to 0, and so on. Correct? Now, using the same concepts that we had used earlier to show that AVK plus 1 to AVN are linearly independent, using the same concept, the same approach, we can say that A star UK plus 1 to A star UN, which are all non-zero and they do not belong to null space of A star because none of them are getting mapped to 0. They do not belong to kernel space of or null space of A star. Then if these are all linear and these are all linearly independent, then we can show that these are also going to be linearly independent, right? Now, in a way, we have shown that uh, this vectors, the vectors that you had vk plus 1 to vn can be written in terms of a star uk plus 1 to a star un, because this is the linearly independent set which belongs to range of A, okay, and they don't belong to null space of A. That means we have this basis of this dimension of vector space V minus the null space of A coming from here. So we can write the vector space V as a summation of range of A star and kernel space of A. Since the intersection is 0, we'll say that this is going to form a direct sum. And when we have the direct sum, we know that dimension of V is going to be equal to dimension of range of A star plus dimension of K of A, right? That's what we had seen earlier. Also, we had shown that the dimension of V is same as dimension of range of A plus dimension of null space of A. From here, from these two inequalities, we can conclude that the dimension of range of A has to be equal to dimension of range of A star. And that is what you would notice that once sort of previously, uh, not in this class, but you must have seen that the matrix A and A transpose have the same rank. That's the reason why they have the same rank. Okay. So we are done with the proof here. Now we go to the next part of the core of this part of linear algebra, which is matrix theory. Now, a matrix is a type of linear transformation, and crudely speaking, it's a collection of numbers arranged in a matrix on a two-dimensional array like this. This is a matrix. But more than that, it's a mapping AX to Y. And it's a linear mapping as shown by this. So Y1 depends linearly on X1, X2 till Xn. And Y2 depends linearly on X1, X2 till Xn. So all of them depend linearly on X1, Xn. And this relation is by this matrix equation. So, one can see A as a linear mapping from Rn space to Rm space, or a complex N space to complex M space. So all the concepts that we had learned previously about linear transformations are applicable to matrices. All the concepts we have learned, you will find them useful here. In particular, we can start by talking about the range of A, this mapping. So range of A we can define as collection of all the vectors Y such that Y is a mapping for all the vectors, mapping of some vector X in Rn space to a vector space Y to a vector Y of Rm space. So we can write the mapping as A such that Rn gets mapped to Rm. Null space is a collection of all the vectors X belonging to Rn such that Ax is 0. The rank of the matrix A can be defined as the dimension of range of A and nullity of the matrix A can be defined as dimension of the kernel of A or null space of A. Right. So now we can look the Venn diagram to see this mapping. So let's say we have the vector space Rn and you're mapping it to Rm. Okay. I'm not saying anything about n, the values of n and m. N can be less than m, n can be greater than m, or n can be equal to m. Anyway, to represent the null space in exactly the same way that we had learned for the linear transformations earlier. So a set of vectors of this vector space are all getting mapped to 0. Okay, so that defines your null space. Okay, the remaining set of vectors, they will map to non-zero vectors in the range of A. We call this as the domain and this as the codomain. The codomain is the entire thing here. Let's say codomain. Okay. And rank of A plus nullity of A, as we had seen earlier, will be equal to dimension of Rn will be equal to n. So rank plus nullity is equal to n. Okay. Now we can write a system of linear equations that you may have that you would like to solve between variables in sort of the equations written in terms of variables ax, and then you know this set of equations. They are all coupled equations. You can write them in the matrix form in this way. Sometimes you will find it useful to represent this entire column as a vector a1. We'll do that very often later on. And this vector, second vector as a2, and let's say this vector is the an vector. Now we can write this equation in terms of vectors a1 to an, which are sometimes called as column vectors, in this way as a linear combination. So we can say x1 times a1 plus x2 times a2 plus x3. This is how we do matrix multiplications. We're just doing exactly that. So if you would expand it and write it this way, we'll get exactly the same way thing. So we see that a linear combination of these vectors a1 to an is what is giving you b. So the problem of solving this equation ax equal to b is essentially solving what you're trying to do is you're trying to find a representation of the vector b and sort of a given vector b in terms of a certain set of vectors a1 to an. Okay, correct? That's what the problem reduces to. So if you know how to represent b in terms of a1 to an, then you would have actually solved, you would know these numbers x1 to xn. That means you would have solved the system of equations ax equal to b. Correct? So now we see that if a1 to an are linearly independent, then we have a unique representation of b in terms of the span of the vectors a1 to an. So b has to belong, first of all, if the solution has to exist, then you should be able to write b in terms of linear combinations of a1 to an. And in that case, b would belong to a vector space which is a span of the vectors a1 to an, which we call as column space of A. Okay, it has to belong to that. And if they are linearly independent, then the solution would be unique. Which is another way, in another way, we are saying that if we add to this set of vectors, if we add B and if we write it like this, then they should be linearly dependent. And at some places you would write you would see this written. Rank of A1 to AN has to be equal to the rank of the augmented matrix, the matrix which has been augmented by adding another column of B to the matrix. The rank has to be same. Okay, that means the range of this matrix has to be same as the range of this matrix. Okay. In another way, we are saying that B, when added, should be linearly dependent on the vectors A1 to AN, and that defines our existence of the solution. That's when the solution would exist. But if your A1 to AN, I mean, your solution would exist, but if A1 to AN are linearly dependent, then clearly there would not be a unique representation of B in terms of A1 to AN, because if they are linearly dependent, then you can always write one of the vectors, let's say AK, as a summation in terms of summations of other vectors I running from 1 to, let's say, N, and I not equal to K with some vector alpha. So let's say alpha I. You can always do that, and if you can do that, then let's say if you were writing B as summation of xi I running from 1 to N, then you can change the representation of AK in here, and that will change this summation, this representation of B in terms of AIs. And that means you will get new numbers x1 to xn, new set of numbers, a different set of numbers x1 to xn, which means that the solution will not be unique. So now you can see this in this way also. Let's say if your summation xi is equal to bi, and because the set is, if we say, is linearly dependent, we are writing it in terms of summation lambda I ai for non-trivial values of lambda I. That means lambda i's are not zero, not all of them are zero. Then we can add, because it's a zero vector, we can add it to this equation, and then you'll get this new equation, which would be summation of xi ai plus summation of lambda I bi. That means you will get summation of xi plus lambda I ai is equal to b vector. And because lambda I cannot take non-trivial values, that means this will also be your new solution, different solution xi prime, which will also be a solution. Which brings you to the thing of sort of conclusion of that there are non-unique solutions, there are infinite solutions. So for any given linear system of equations Ax is equal to B, there are three possibilities: A, unique solution, number of solutions is 1, and if it is not 1 or 0, then it has to be infinite. You cannot say I have only three solutions, three different solutions for this system. You have either infinite, 1, or no solutions. If B does not belong to the column space of A, then you have no solution. If the vectors or the column vectors of A are all linearly independent, then you have unique solution. And if they are linearly dependent, then they are infinite solutions. In other words, what we are saying is that the column space, or is essentially the dimension of this mapping A to B, has more than is greater than equal to 0. The null space of A has dimensions more than greater than equal to 1, right? So again, the same thing, whatever we sort of saw here, this side, we can sort of see it in another way as following. We can say, let's say, if dimension of null space of A is greater than equal to 1, that means there are a set of vectors which are not 0, but they get mapped to 0. There are some vectors Axn. Now you have Ax equal to B also. You can add these two equations. When you add these two equations, you get a new equation which is Ax plus Xn equal to B. That means if X is a solution, then your X plus Xn is also a solution, right? And because if dimension is more than, if xn belongs to k of a, then lambda times xn will also belong to k of a, correct? And that means you have infinite set of vectors that can form this solution, right? Because lambda can take any value. So this gives you infinite solutions. Now, but they are infinite, but in a certain way. So what is that certain way? So if you can find a particular solution, let's say x is not, okay, which does not belong to k of a. Okay, some particular solution you can find, some mapping, which was satisfying, let's say, which you found one particular vector which was getting mapped to p vector. Okay, then you can add another set of vectors which belong to k of a. So this will be the form of your infinite solutions. Particular solution plus infinite solution, right? That's what it means. Now, when we talk about solution of linear differential equations, what we say is L of y, some differential operator of y, is equal to, let's say, a function of x, right? Then we say that if we can find a solution to the homogeneous equation, that means the null space of this operator L, and if we can find a particular solution which is f of x, which is going to be this, and the form of the equation then reduces to y. Solution is essentially that homogeneous uh, solution plus the particular solution. So this is exactly the same concept there. Anyway, as long as you don't specify the conditions, boundary conditions or initial conditions, you'll have infinite solutions in terms of the coefficients of this cy1 plus c2y2 that you get. So you can see these also as mappings in the function space. Anyway, moving on, we see that we had listed on a system of equations. Clearly, this system of equations, you can have equation 1 equal to 0, equation 1 equal to, let's say, y1, equation 2 equal to y2, and so on. You have these set of equations, right? I can arrange in them in a different way. We can say that the same system can be written as equation of 2 equal to y1, y2 first, equation of 1 equal to y1, and that will not change the system of equations. That means if I change the order of the equations, if, which is now if I'm writing in the matrix form, and what I'm doing is I'm going to exchange the rows. That's what looking at different equations would mean. So if you change the rows of the matrix A, divide this way, y1 to y2 and so on. Of course, you'll have to change the row of the y vector also correspondingly. Okay, so if you make these changes in A and y vector, your system of equations will remain unchanged, right? That means the matrix representation, the basic nature of the matrix representation will not change. The mapping ax equal to y is not going to change. It is just that you have chosen for your range of A, you've chosen a different coordinate. That's what it would mean. You've changed the naming of the coordinates. You can think of it like that. Same way, if I scale an equation, so if I scale one of the equations and scale the corresponding y component, that will not change the equation. So that's like scaling of rows. It doesn't change the nature of the mapping ax equal to y. If I add equations, that means if I add rows to each other, that means putting together the first 2 points, adding and scaling and exchanging put together, that will also not change the equation. I can add equation 1 and 2 and write one equation as one of the two equations as equation 1 plus equation 2 is equal to y1 plus y2. One thing to note is that all these changes that I'm doing to the matrix A have to be done to the right hand side also. Now, they do not change, as I said, they do not change the solutions, and therefore they're called elementary operations, or you can think of them whatever we have discussed. We have talked about row operations, exchange of rows, scaling of rows, adding of rows. There are elementary row operations, and they don't change the nature of the mapping Ax to Y. Or in other words, they do not change the rank also. Or you can think of it as the solvability of the system of equations is not altered by doing these operations. If Ax equal to Y was solvable, then A prime obtained by doing these operations, A prime x equal to Y prime, is also solvable. Now, just the row operations, but suppose if I can bring changes in the columns also, but then that would mean that I'm exchanging. When I look at Ax, then I think somewhere we had written it as x1 a1, x2 a2, and so on. So if I change two of these, what I'm doing is I'm also changing, I have to change the corresponding x2 and x1 also, right, to get the same set of equations. So I can make the changes to columns also in the same way as I could change the rows, but then I have to keep in mind that I have to exchange the variable locations also. Okay, I can scale one of the variables, and the corresponding row column will also get scaled. I can modify the variables as I want to write x1 plus x2 as a new variable x1 prime because I see some that would make it easy for me to solve. So I can do that also. That means I can add columns also. So these are called elementary column operations. You can think of them as elementary column operations. So as you saw that elementary row operations, you have to change y. Elementary column operations, you have to change x. Okay, so this will keep in mind. In other ways, we can also think of it as changing the basis of y or changing the basis of x, the mapped space x. So now we'll take an example. Let's take an example of this matrix, which is 3 cross 4. It has 3 rows and 4 columns. And we modify this using the elementary row operations and column operations in this way. We say that the row 3 is essentially row 3 plus A times row 2. So that would mean that row 3 is essentially 3 plus A times row 2, which is 2A, is the first element. Then you have minus 1 and minus 4A. Then you have 0, minus A, and then you have 3 plus 0 times A, so 3 plus 0, which gives you this matrix with the modified row. Now we perform column operations on this. We'll say column, we're doing it in an order 1 and 2. So column 2 is here, and take this A times column 3 has to be subtracted and placed here. Okay, so column 2 1 minus A times 0 will give you 1. Column 2 minus 4 and minus times A into minus 1 plus A. And here you have minus 1 minus 4a as column 2 and minus a multiplied by minus a and added to column 2, a square. So you get the modified matrix. Okay. Now, what we have done in other ways is that we started with the system Ax equal to b, but we have modified by performing these row operations. I have modified b. Suppose we want to see these operations as matrix multiplications, and these whatever we performed here, if I can perform it using by multiplying A with the matrix. So you can write this as R of A as the modified matrix by row operations will be equal to R times B, the same operations being performed on the right hand side. Same way I can modify the representation of the x vector by using this matrix C times x prime, which will be like modifying A by performing column operations. So now the modified equation would look like something like A prime x prime is B prime, right? Or you can think of it as where A prime would be essentially given by doing column operations on A, row operations on A, and column operations on A. This is how you obtain A prime. Now we can see this as change of basis or as another mapping. So you get x from x prime, you can think of getting to C, and this has to be invertible. So essentially this has to be one-to-one mapping. That means if you want to go back, you can go back to know exactly where you have come from using the C inverse mapping. If it's a one-to-one mapping, then it's invertible also. One-to-one and onto is invertible mapping. So you can define C inverse also. C inverse would exist. So these operations are essentially pre and post multiplying the matrix A with matrices R and C respectively. So now we'll sort of, to get these matrices R and A, for the example that we had taken, we can start by looking at these matrices, which is M cross M, where M in this case is 3, because we were looking at a matrix 3 cross 4. So IM, which is pre-multiplying it, has to have dimensions of 3 cross 3. We are doing row operations. We do the row operation on this identity matrix. We get row of 3 is essentially row of 3 plus A times row of 2. So that gives you this modified matrix, identity matrix, and that you denote by, let's say, E1. Now, similarly, you can get for the post multiplication, now n has to be 4. So it's a 4 cross 4 matrix, and you do the column operation and you get the E2 matrix. Okay. So now what we do is we look at the representation, this modified uh, uh, by row, elementary row and column operation matrix. We can look at it as E1 times A E2, and when we do this multiplication, you will get the matrix that you got by performing row and column operations. And that also gives us essentially the mappings x to x prime and y to y prime. So you can see this as Ax equal to y is a system that we started with. Now I'm writing a Cx prime as Ry prime. Then I can think of that I take the inverse because R has to be invertible. This mapping is invertible mapping, 1 to 1 and 1 to 2. This also is, it's like change of basis. You can think of it like as change of basis. And so it has to be invertible matrix. you get R inverse AC, and now you get the modified system A prime X prime is equal to Y prime, and A prime now is given by R prime R inverse AC. Now suppose if the domain and codomain were same, let's say if you are mapping a 4D space to a 4D space, four-dimensional space, right? Then if I change the basis for this and I also change the basis for this, and I choose that for this representation, if I'm changing x by writing it as c times x prime, then I also change y by the same representation, the same basis I'm using for both vector spaces. If that is the case, then r is equal to c, and what you get is a prime is going to be c inverse ac. That is something called a similarity transformation. And these matrices that you'll get A and A prime, they're called similar matrices, and then you represent them as A is similar to A prime. This is the symbol that you use for denoting the similarity transformation or to denote the similar matrices. Some places you will find a matrix A written as similar to a diagonal matrix. That means you could, by doing this transformation, you could reduce A to a diagonal matrix. These are called diagonalizable matrices that we'll talk about later. So the matrix A can be similar to a diagonal matrix. That means only the diagonal entries are non-zero, other entries are zero. Now imagine if you have a diagonal matrix D x prime is equal to Y prime, you're saying D11 x prime 1 is Y1 prime. Right? You have D22 x2 prime is equal to Y2 prime. So in principle, you have already gotten the solution as x1 prime is y1 prime by d11, x2 prime is y2 prime by d22. So a system of equations which is just the diagonal made by diagonal matrices are easily solvable, are readily solvable. And therefore, in numerical linear algebra, the goal is normally to bring A to as close as you can bring it to D. That is normally what the goal is. Now moving on, we look at the this how to get inverse of the matrix A. So for that to happen, it has to be a one-to-one and onto transformation. So given system Ax equal to B, where x belongs to Rn and y belongs to B belongs to Rn. So it has to be one-to-one onto mapping. What you do is, if we can, by performing some operations, row operations, let's say P1 to Pn, some row operations, some elementary operations, and we are talking about pre-multiplying, that means we are talking about row operations. So if we can perform these row operations on A, such that eventually you are able to reduce it to an identity matrix by performing these row operations, then your A inverse, you can write it write as product of these transformations, right? That's what it would mean. It means if this was A inverse, then A inverse A into A will become identity matrix, which is like this. So you can write your A inverse as product of these elementary row operation matrices. Now let's to show this, let's consider a matrix in this form. It's a 3 cross 3 matrix. Okay, now we perform these elementary row operations, and we perform only row operations, and we'll keep track of these row operations by performing them on starting with an identity matrix on the right. That's what I think was taught to you, and this is exactly what you were doing earlier, but maybe the reason was not clear. Now the reason has become clear here. So you start with the A matrix here, you start with the identity matrix here, then you perform row operations. And when you perform row operation, you start from the first row such that, and you try to bring down all the numbers that you have below that first element of the row to 0. So in this case, we see that we can modify row 2 by adding 2 times row 1 to it, and we perform the same operation on the identity matrix here. So now you have reduced these two numbers to 0, and you have obtained, this is our P1 matrix. Okay. Now if you perform another operation P2 on this, that will be modifying P1 with P2, and then you'll get product of P2 into P1 on this side. Okay. So we think, yeah. So now we perform the next operation such that every element below this number is turned to 0, and that you do by making this operation. So if we go back and look at this term, if we multiply this equation by 1 by 9 and subtract this and modify this row, then you get a 0 here. That's what we have done here. Row 3 has been modified in a way by subtracting row 2 by 9. We get a 0, and we have performed the same operation here. So we have obtained P1 into P2. Now we perform 2 more operations, trying to reduce. Now once you have reduced it into a lower diagonal matrix, you try to reduce it into a diagonal matrix if it is diagonalizable. That is a condition. In this case, as we will see, it will become diagonalizable. So we sort of try to bring these 3 numbers, 3, 0, and 1 to 0. We start from the bottom row and go upwards now to do this. We perform this operation on row 2 first, and then we also scale the row 3 matrix. So you get 1 here because we want to reduce it into an identity matrix. So we start making numbers as 1. When the same these 2 operations, 3 and 4 row operations, have been performed on the second part, you are doing essentially P2, P3, and P4. That's what you have obtained. And by doing another 2 sets of these row operations, R2 as R2 by 9, we have scaled this number to 1. These 2 have been reduced to 0. Now the only task is to reduce this number 3 to 0, and that you do by subtracting row 1 from 3. You subtract 3 times row 2 from row 1 and replace row 1. That, and we perform the same these 2 operations on this also. So what you've done is you have P2, P3, P4 they were already done. You've done P5 and P6 also. So you've obtained this, and by doing these row operations, you have reduced the matrix A to an identity matrix. Note that we cannot do it always, but in this case, we have been able to do. Now we see that we've reduced A inverse. I'll just sort of clarify that. No, I think we can always do this to get A inverse. We can always perform row operations, but I would like to clarify that these are not similarity transformations. These are not similarity transformations. So you have reduced a matrix A to a diagonal matrix by performing only row operations, but these are not similarity transformations. And this, if A is invertible, then you can always do this. So this is always possible, yes. Okay, but if you're doing similarity transformation, A, C inverse C, then this may not be able to, you may not be able to reduce to a diagonal form. Okay, this is what you need to remember. So I'll clarify myself there, yes. Okay, so you get A inverse, which is now a product of these matrices, P1 to P6. And that's why you could actually reduce A to identity matrix. Now, in the I'll sort of this is one way that you already knew, I guess, how to get inverses. So, just on the way, we came across a stage where we could reduce by performing P1 and P2, we could reduce the matrix A into an upper rectangular matrix like this, in an upper triangular matrix. In an upper triangular matrix, we could reduce. So, essentially what you did was you multiplied A with pre-multiplied by P1, P2, and you could reduce it to U. Now P to P1, as you see, it will always be something like a lower triangular matrix. That's what you notice. And so this is a lower triangular matrix. Interestingly, the inverse, if you will take of this matrix, you'll get A as P2, P1 inverse into U. One property of lower triangular matrices is that the inverse is also a lower triangular matrix that you can show. And essentially what you have done is you've reduced A into a product of two matrices, one lower triangular matrix and one upper triangular matrix. And that's what we call as LU decomposition. So our matrix A can always be reduced to this LU decomposition can be performed on it. Okay. So we'll stop here, and next time we'll continue working with matrices in the matrix theory. We'll sort of learn about some more topics.